Thank you very much, sir. I guess my screen is visible. Okay. Thank you very much. Very good afternoon to everyone. As Dr. Guru Prasad sir has introduced, myself Basavanagowda, and I'm working as an assistant professor in Department of Civil Engineering, Bangalore, Ramaiah Institute of Technology, Bangalore. Now here I'm presenting a few cases which I worked on the site-specific response analysis. In my presentation, first I would like to introduce what is soil amplification, why you need to study about the soil amplification, and what are its effects on the structures. Then how do we measure the soil amplification, or the what you'll call it as site-specific response analysis. Now let me move on to the actual content. So here the definition of soil amplification is, as everyone knows, it's increase in the ground motion at the soil surface when you compare with the motion at the bedrock. Now to have a better understanding, I'll just place this video. After playing this, I would like to continue my presentation. I request all the audience to listen to this. Sorry. One second. Sorry for interruption. Thanks. Yeah. Yeah, thank you for watching. What is the point I wanted to discuss here is, you would have seen the amplification of the waves when you consider the hard strata and when you consider the soft strata. When the in fact the video shows the surface waves, but when we speak about the shear waves, they start originating from the focal points, or what you call it as a focus, or what you can call it as a location of the epicenter, where when they reach the ground surface, depending on the surface through which they pass in their amplitudes, or they may so these wave motions will affect the structures resting on the ground surface. That is what is called as a soil amplification. You can see the wave motion here. When they pass through the solid bedrocks, you will have a very less amplitude. Again, when they pass through the poorly consolidated sediment, again you will find an increase in the wave amplitudes. Again, when they pass through the solid bedrock, sediments or water saturated sand and mud, you can notice that there is an enormous increase in the amplitude of the wave motion. So this will affect the structures resting on the ground surface. So some of the examples they have shown here, one is the landslide potential, another one is either you can have a phenomenon of amplification of the waves or liquefaction of the ground surface can happen. So here mild amplification and strong, you can say moderate and strong. Here what you can see is the complete liquefaction of the soil mass. But in my today's lecture, I'll restrict only myself to the soil amplification. So I'll not touch upon the liquefaction part. Now, why the soil amplifies? As I mentioned earlier, as the seismic waves travel faster through the hard rocks than through the soft rocks or the sediments, that means again the waves passes from deeper, harder to shallow, softer rocks. They slow down and gets bigger in their amplitudes as the energy piles up. So amplification of waves is more in case of your softer soils than compared to the stiff soils. Now, when you encounter the water table in this, especially when you come across water table present maybe at the ground level or maybe at a lower level, then this phenomenon of amplification will be quite complex. Now, what is the influence of this soil amplification on the structure? We all know that we are going to construct different types of structures like nuclear power plants, or maybe nowadays you can see that so many metro stations or metro works are going on in and around India. So everywhere, this soil amplification will affect the structures resting on the ground. So the response of the structure is essentially a function of regional seismicity, the nature of source mechanism, geology, and the local soil conditions. Here, the basic problems what we have to solve by the geotechnical engineer is we have to first estimate what are the effects of these earthquake hazards. Local soil conditions. Second, my volume is low. Somebody is commenting. Sorry. I've just kept maximum in my system. Okay. So the ground motion amplification, local soil conditions like what type of sediment through which the soil, the waves, shear waves are passing through, and at what depth the bedrock is available, and what is the magnitude of the earthquake which is happening at a particular place. All these factors will affects the soil amplification. So as I mentioned earlier, soft sediments or the loose strata, what you can call it as, they can very easily damage the structures resting on the ground level. See, ground motion amplification can cause subsequent ground failures as a one such phenomenon as the liquefaction, structural failures, or landslides due to the excessive ground shaking. Now, in continuation of that, what I explained, so during the strong earthquakes, seismic waves traveling towards the ground surface, they alter the engineering characteristics of the soil layers, and consequently, the characteristics of the traveling seismic waves will also increase the peak ground accelerations. Now, maybe many of you would have aware that most of the cities, many earthquake-prone cities are settled over very susceptible areas with a very young deposits. If I can give you some example, Mexico City, and Loma Prieta. They are resting on a very young deposits. These deposits may be due to the weathering action, maybe slowly they may be having a very loose strata. So I can say that they are prone to the earthquakes. Now, as a result of this, the damage what is created by these shear waves is very devastating, I can say. So this amplification study is very much required, to any what you can call it as soil parameters, possibilities of any liquefaction, or estimate, increase in the peak ground acceleration. All those things you need to study. Now, as I spoke earlier, this will be useful. The study of soil amplification will be useful as an engineer or any professional which belongs to civil engineering fraternity. We can estimate what is the site natural periods, what is the fundamental natural period of these structures. We can easily assess depending upon the soil amplification. So the next thing is we can estimate what is the peak ground acceleration, because once some earthquake happens at a bedrock level, depending on the soil layer through which it transfers, there may be an increase in the acceleration or maybe a decrease in the acceleration. So whatever we get at the ground level, that we need to estimate, and based on the peak ground acceleration, we have to create the response spectra, and that can be used for either time history analysis or response spectrum analysis. But we have the habit of following IS 1893. They have given codal, they have given the response spectrum curve to be followed for the three different types of soils. That is the general graph what we have. To be honest, or to be strictly speaking, you, depending on the site condition, you have to perform the site specific response analysis, and that should be used as a input for your STAD analysis or ETAPS analysis. That can be used as an input for your time history analysis. Now, for structural engineering, structural engineers with various parameters, primarily response spectra for design and safety evaluation of the structures. So again, this is important for the structural engineers. They are discussing with the, they are dealing with the response spectra. So this amplification study will gives you what is the response spectra for a particular site. Now, as I mentioned, in the design of very important structures like nuclear power plants or metro rail bridges, tall structures and chimneys, whenever you do the design of these structures, understanding the soil properties below the ground is very important. We have to do the site characterization. We have to find out what is the peak ground acceleration, and for that you have to design your structures. Now, in soil structure interaction analysis, peak acceleration values at the bedrock level and at the surface levels, especially when the water table is present, is very important. That we have to consider. Yeah, now I mentioned that soil amplification will happen and why you have to study everything. But there are some factors which can affect the site-specific response. Site-specific response, what factors can affect the site-specific response is horizontal extent and the depth of soil overlying the bedrock. What type of soil is above the bedrock level? Sometimes you will have slopes of the bedding planes of the soils overlying the bedrock. So there, it's very difficult to estimate the site-specific response sometimes, and changes of the soil types horizontally, the change in the soil profile. Especially if I have a layered soil, definitely it becomes very difficult to perform the site-specific response analysis, and you would have seen that all the soil layers are not exactly horizontal. Okay, so then you cannot give it as a 2 meter thickness exactly horizontal. No, this is not possible. In fact, in the site, when you go to a particular place, the soil layers would not have been exactly horizontal. If there is any variations in the depth or thickness of the soil profile, definitely it will affect your site-specific response. And what is the topography of the bedrock and the deposited soil and deposited soils and faults crossing the soil deposits. So these factors will affect our site-specific response. Now, as I mentioned, I'll be concentrating in this presentation only on the site-specific response analysis. Now, what all the steps we are going to follow in this site-specific response analysis? This I've referred from Govindraj et al. That is the paper with the help of which we performed this site-specific response analysis. Characterization of the site. Characterization is nothing but what type of soil is there, what is its elastic modulus, and what is the density of the soil, and what is the depth at which the water table is present, and what is the shear modulus of the soil, thickness of the soil is. All these data has to be collected. You can get it easily from any of the borehole methods. You can conduct the SPT, CPT, everything from that. You can extract what is the properties of the soil profile, I mean parameters of the soil. Now, once you're done with the characterization of the site, you have to select a suitable input bedrock motion. If you see, most of the cities would not have come across major earthquakes in the past. Then it is very difficult to do select appropriate rock motions, that is natural analysis for that particular place. Natural acceleration time histories are selected to represent the design rock motions for the site. Maybe in the coming, and what is the output at the surface level, that should be collected. Okay, so this output you have to give it as a as an input for the response spectrum analysis. Now, next, site-specific response spectra for a structural analysis. Now, response spectra of a calculated ground surface motion are statically analyzed to develop the design spectra. Once you get the response spectra for a particular ground surface, you can easily construct the design spectra for that site. Am I audible to everyone? Hello? Am I audible to everyone? Okay, thank you. Yeah. Whenever we do this ground response or site specific response analysis, we do some assumptions in the one dimension analysis. Okay, so what are those assumptions? Let us see. We assume that the soil layers are exactly horizontal and they extend to the infinite depths. And the second one is the ground surface is level. The response in these systems are caused by the upward propagation of the shear waves from the underlying rock formation. That means waves will propagate from the bedrock and they travel towards the ground surface. Now, each layer is in the system is defined by a value of shear modulus, critical damping ratio, density, and thickness. These are independent of the frequency. We are assuming that each layer is defined by a particular value of shear modulus depending on the velocity, wave velocity, and what is the critical damping ratio, density, etc. We are giving this analysis input for the one-dimensional analysis. Now we have some of the methods by which we can conduct the site-specific response analysis. Sorry, please excuse me. Echo ಆಗ್ತಿದೆ. Mute ಮಾಡಿ ನೀವು. So experimental methods, if I can speak about, one is standard spectral ratio methods and micro tremor methods. These are some of the experimental methods what we have to conduct the site-specific response analysis. Now, some of the numerical methods what we have, one-dimensional, if I can speak, I can use Shake software, Deep Soil software, EduShake, what we can call it as ProShake, etc. These are for the one-dimensional analysis. Now, for the two-dimensional analysis, you can use FLAC 2D, Flaxus 2D, Quake, etc. Fast Lagrangian analysis of continuum model, what we call it as. You can perform in both 2D and 3D. Okay, again, Flaxus also you can do it in 2D or 3D. So these are some of the methods with which we can conduct the site-specific response analysis. Now, my focus in this presentation is I've considered one of the example for this micro tremor studies. How do we do that? And then I'll move on to the one-dimension analysis. I'm not focusing on 2D and 3D analysis. Okay, I'll be touching upon the micro tremor studies. How do we do that? And one-dimension analysis. I'll be explaining about the Shake and the Deep Soil software. How do we use that? Now, one case study I've considered, which we conducted in Bangalore city, India. Okay, Karnataka state, what you can call it as. Now, that is application of refraction micro tremor. That is called as a REMI. REMI is the name of the equipment, what we call it as. Application of refraction micro tremor for seismic site characterization. I've just quoted the reference number. At the end of my presentation, you have a reference list. There you can check this paper. We have explained how do we use the REMI for the seismic site characterization. You can just go through that. Now, I'll give you a brief introduction about what is microtremor, how it works, everything. Uh, if you have seen that existing conventional methods for determining the shallow shear velocity structure of a given subsurface requires drilling to determine what is the shear velocity. You have to do the drilling work, you have to extract the soil sample. Depending on the soil sample, what you calculated, you will go for determining the soil properties. Now, drillings are laborious. You know that drilling requires so much time and it becomes sometimes uneconomical also. Further, the process becomes increasingly difficult in the populated areas where there will be several constraints to carry out the experimental investigations. Then you can resort these microtremor studies. Now, shear wave velocity may be obtained directly or indirectly using variety of methods. Okay, if I can name some of the indirect methods like SPT or CPT, results may be less reliable and provides limited depth of exploration compared to the results obtained by measuring the seismic energy directly. You know, if you can consider the cases of say this micro tremor studies, we can even go to a depth of 100 meters below the ground level. That is the advantage what we have with respect to this micro tremor studies. Now, to overcome this problem, a method has been developed to use the seismic noise or micro tremor to map the shallow shear wave velocity structure. This is known as REMI, or what we call it as refraction micro tremor method. The major benefits in using the REMI method includes the ability to collect the data quickly with a two-person crew and the ability to collect the seismic data in a noisy urban environment. You can perform this test even in a noisy environment, and a maximum of 2 people are required to carry out this experiment. That with that advantage, you can conduct this refraction microtremor studies. We have another few more microtremor studies, what we call it as SASW, and that is surface wave analysis method, SASW method, and another one is MASW method. SASW, MASW, another one is this refraction microtremor methods. These three methods you can use to carry out the seismic site characterization. If you can have a look at this, this is the data acquisition system what you are seeing here, and a battery connected to the laptop, and you can see the recordings what you have. And here in the right side of the screen, I've shown these are the connected geophones. These are called as the geophones, and these there are about 12 in numbers. Usually, sometimes we use 8 numbers of geophones depending on the land or the site, how much we have to do the site characterization. Accordingly, you can use the numbers. It varies from 8 to 12. So these geophones are connected to this data acquisition system, and the data will get stored here. The processing, everything will be done, and we will get the shear velocity plot, ready-made shear velocity plot. If I can give you the clear picture, we conducted one study in Central Power Research Institute, Bangalore. We have placed the refraction microtremor equipment along the roadsides, where the vibrations are created with the help of vehicular movement, or even the movement of the people, also human beings, that can also be observed by these geophones. Again, this is a closer view. With the help of these two, we will connect to the main cable. Like this, you will have a 8 to 12 geophones connected to the main cable. And these are the recordings what we get it from the geophones. And this is the instrument, or the what we'll call it as a data acquisition, or the software which will process these refraction microtremor geophone signals, what we call it as a Vibroscope software. And there are about 12 readings here. These readings are obtained directly from the geophones. We'll subject this for a further filtering process, and we will collect what is the shear velocity after this processing. Maybe if possible, I'll show you how do we how do we get the plot of shear wave velocity. Now, shear wave velocities are characterized at the site using the REMI technique. Okay, the essence of this technique is that ambient noise contains usable signals that are predictable from velocity structure that may be presumably caused by the human activities. As I mentioned, even a small human activity can also create some noises that can be easily detected by these geophones. The vertical component of the ambient noise dominated by the Rayleigh waves is recorded by the geophones or seismographs array, what we can call it as, and either geophones you can call it as, or seismographs. Now, these Rayleigh waves, I think many of the speakers have already discussed what are Rayleigh waves and what are love waves, what are shear waves in the earlier sessions. Now, I'll not go into that. My interest is only how do we collect the data from the REMI equipment, and how do we further process it. Now, these Rayleigh waves are separated from the other wave arrivals using a two-dimensional slowness frequency transforms. The image what we collect it, that is what is called as slowness frequency transform of noise records. Energy propagating in both directions is analyzed. The fundamental mode phase velocity of Rayleigh wave dispersion is picked along the minimum velocity envelope of the energy within the slowness frequency spectral image. Now, these Rayleigh wave dispersion peaks are then interactively modeled using trial and error adjustments of the velocity depth model to obtain the shear wave velocity versus depth profile. Modeling was done using CSOPT REMI. This is the data acquisition system name, what we call it as CSOPT REMI. I'm not in a position to share much of the details with respect to this data acquisition system. This is what the PF image, what we call it as. PF means slowness frequency image, what we call it as. The method uses the surface waves recorded on the standard multi-geophone seismic refraction equipment. You can see we have selected some color bands based on which the shear wave velocity mapping will be done here. Here, it will give you what is the variation of the shear wave velocity with respect to depths. Accordingly, whatever the software will give you what color code you have to pick. Once you pick that color code, by default, it will display what is the velocity value of shear wave velocity at a particular depth. You can see we have made a comparison with the velocity obtained from the standard penetration test, and we have compared with the refraction microtremor results. They are in close agreement. One advantage, as I mentioned earlier, is in your standard penetration test, the drilling will stop, say, maximum depth of 30 meter, but with the help of refraction microtremor, even you can go to a depth of 100 meters. Okay, but most of the construction activities, they require only what is the an average shear wave velocity at 30 meter depth. That what we call it as VS30. This is the shear wave velocity mapping for a Vijayanagar site. This is a metro station. What we have, Vijayanagar metro station. Near that, we carried out this refraction microtremor study, and we have plotted what is the maximum velocity at a depth of 30 meter. Okay. Yeah. Along with the seismic site characterization, we did the liquefaction potential analysis. Now we have used some of the terminologies here. If somebody would have studied this earlier, you will be having some idea what is cyclic stress ratio. Cyclic stress ratio at a particular depth, it is it's the amount of repeated loading which is acting on this particular soil mass, what we call it as. Now, as defined by Seed and Idris in the year 1971, we defined the cyclic stress ratio like this. I've just given the details. What is tau AV is the average equivalent uniform cyclic shear stress, and Amax is the maximum peak ground horizontal acceleration, surface acceleration during the earthquakes. And we are calculating what is the effective overburden stress and total overburden stress at that particular depths. Okay, and RD is the shear stress reduction factor. For the details of this, I request you to kindly go through the paper what I mentioned earlier. I mentioned in the reference number, that is reference number 9. I've just mentioned all the details of this. Based on the study, what we did, this is the depth at which we calculated what is the corresponding shear wave velocity. And this is the boundary line which defines a particular place is susceptible to liquefaction or not. As mentioned in Anderson-Stokey in the year 1999, the boundary line separating liquefiable and non-liquefiable region is the cyclic resistance ratio, what we call it as. So this is that boundary line, and most of the points what we measured, they're beyond this boundary line. So thereby we can say that all these sites, we conducted about 3-4 studies in and around Bangalore. Wherever we have a metro stations, there we conducted, but I'm placing only on record only one of the site test results here. So most of the places, they are free from liquefaction phenomena. What we did in Bangalore. Now, coming to the ground response analysis, here I just discussed on the liquefaction potential analysis. We did some ground response analysis also. Now, the problem what we faced here is we didn't had any magnitude earthquakes, previously recorded earthquakes, and no strong ground motion records were available in the study site. We did this in way back 2011. So you know that as per IS 1893-2002, the classification was zone 1, that is with the 0.10 with the zone factor. And some of the studies, Sitaram et al., they have conducted some studies, and they concluded that maximum earthquake magnitude in the year, I think if I can remember properly, maybe in 2015 or 16, they gave this. I mean, maybe in 2011 or 12, it seems. I'm not able to remember that year. They have given that this magnitude, maximum magnitude of the earthquake, what we can expect was between say 6 to 7.5. So what we did is we gone through the equivalent linear one-dimensional ground response analysis that is called as a Shake 2000, which was developed by Idris and Son in the year 2004. We use this to carry out our ground response analysis. So this is one software where it will give you the time history analysis, response acceleration time history. When you give the acceleration time history at the ground level, I mean at the bedrock level, it will give you the sites. So we use another method, that is wavelet based method has been used for the generation of spectrum compatibility time history analysis for the earthquake. I'll be discussing on this. So this is the acceleration time history what we used. Since there were no records available for the ground response analysis at that time, we used a Kolinga earthquake. We searched in the earthquake research database, peer what we call it as. When we gone through that, we got this Kolinga earthquake, which is having similar magnitudes and similar peak ground acceleration as suggested by Sitaram et al. We collected this earthquake and we have given this as an input. And this is the amplification ratio what we got it for a Vijayanagar side, where we did the micro tremor studies. And we plotted what is the peak ground acceleration also with respect to depths. This is what the variation of the peak ground acceleration we got around 4.44 g. That is what the I think maximum peak ground acceleration what we got it at the ground level is 0.44 g. Okay, so it started from around 0.1 or 0.12. It went on about 0.45 g. That is the we went nearly about 45 meter below the ground level with the help of refraction microtremor. We calculated what is the peak ground acceleration. So this is the spectral acceleration what we generated from the Shake software and the response spectrum matching software. So response spectrum matching software is another wavelet based method what we can use to generate this spectral acceleration graphs. One-dimensional ground response analysis carried out at different locations revealed that peak ground acceleration at the surface ranges from 0.3 to 0.44 g. As I mentioned, we selected 3 to 4 sites in the Bangalore city. We conducted this refraction microtremor studies, and the maximum peak values what we got is around between 0.3 to 0.44 g. Maximum spectral acceleration of 2.07 g has been observed at Vijayanagar site, and the corresponding period was 0.17 seconds, which is equivalent to 5.48 hertz. Now, whatever the softwares I mentioned here, I've not discussed here, but I'll be discussing what all those software, what is Shake 2000 is, and what is this wavelet-based method in the coming slides. Maybe here I can discuss that. Now, this is another study what we conducted in Bangalore again. This is site-specific response analysis or metro rail bridge. What we did here is below the ground level, we did refraction microtremor studies, and this is based on the Shake 2000 software. So what is this studies? What is this study? I'll just give you the brief introduction. This is the study which we conducted near Chinnaswamy Cricket Stadium in Bangalore City, based on the soil prototype, soil profile type reported by the downwell test. We collected the downwell test from the consultant who was working on this construction activity. We collected the downwell test data from them. We used the soil profile and we carried out the site specific response spectra. And this Shake 2000 software we are using to perform one-dimensional equivalent linear approach analysis. Now we evaluate response analysis using Ramaiah of the China Cricket Stadium. We evaluated what are acceleration, spectral acceleration values. And metro rail bridge structure has been analyzed for 3 different support conditions, and each model has been analyzed for equivalent stack. Maybe in the next slide, I'll be showing you what is the structures, how they are placed. Okay, and the 3 different conditions we have done the evaluation. One is bridge pier supporting a fixed base, bridge pier supporting a pile foundation, bridge pier supporting with the response analysis. So this is the location of the borehole where what we did. The naming was given as AB14, and this is the place where we did the seismic downhole test. So okay, so these are the pictures what I was mentioning in the previous slides. This is the typical metro rail bridge cross section with the conventional fixed base support. Okay, so this is the fixed base analysis what we did. And this is again with the pile support, typical metro rail bridge cross section with the pile support. You can see the depth of the height of the pier. It was almost around 12 meters. Okay, so the details has been given here, and just have a look at it. So this is another cross section of the metro rail bridge cross section with underground station box support. This is the box support with the help of which they built this metro tunneling where they constructed this metro pillar or the pier segment, what we call it as typical metro rail bridge cross section with underground station box support. Okay, so the details they have given here. Below the ground level, they have gone to a depth of about nearly 14 to 16 meter below the ground level. They have to construct this a concrete box structure, and they have erected this pier segment above that. Now, these are the details of the soil profile which we have collected from the geotechnical investigations at the tunnel locations. CEC Soma is the client who has performed this downhole test measurements, and when they did this, and what is the depth below the ground level, everything, what are the details below the ground level is shown here. Again, we have gone to a depth of 21.8 meters. AB14 terminated at 21.8 meter below the ground level. Okay, so these are some of the details of the soil profile what we encountered at the site. Now, as I mentioned about Shake 2000, this Shake 2000 in equivalent linear one-dimensional ground response analysis, in which motion of the object can be given in any one layer of the system, and motion can be computed in any other layer. Suppose if you give the motion, bedrock motion, then you can collect what is the acceleration time history response at a intermediate layer or maybe at the ground surface. That is the advantage what we have with respect to Shake 2000. Maybe someone would have already used it, then they will have a better idea of this. So the basic approach of one-dimensional site response study is the vertical propagation of the shear waves through soil layers lying on an elastic layer of rock which extends in infinite depths. Okay, so the rock motion obtained from synthetic ground motion model using RSP Mesh 2005 is assigned at the bedrock level as input in Shake 2000 to evaluate the peak acceleration values and acceleration time histories at the top of each sublayer. Okay, so this is the methodology what is involved here in the Shake 2000. Now, before we get into the Shake 2000 procedure, as an input for this Shake 2000, we needed the dynamic properties at that particular place where we did the site-specific analysis of the metro rail bridge. For that, for a given, we report to IS 5249/1992. For a given seismic event, the response of the earth structure strongly depends on the dynamic properties of the soil. The dynamic properties were defined by the damping ratio and shear modulus degradation curves. Such curves were developed for different soil materials. For example, curves for sand and clay were proposed by Seed and Idris and Seed and Son. And for gravel, Seed et al. And G by G Max rock. Again, Seed and Idris, they have given three curves for lower, upper bound, and average values. So we have made use of these curves what is defined by the different persons who has worked on this. So as an input for the Shake 2000, we wanted the what is the elastic modulus of the soil. We have made use of this equation, that is shear modulus equation, as per the code I mentioned earlier. This is the shear wave velocity what we have. Okay, this is shear wave velocity, and this is what you can call it as a Poisson's ratio. What value of Poisson's ratio you have to consider is given here. What type of soil and what is the maximum value of the Poisson's ratio you can consider. We have calculated what is the elastic modulus of the soil with the help of this equation, and small strain shear modulus of the soil has been estimated using this, that is shear modulus. Once we know the shear wave velocity with the help of downward test, and if we know the density, we can easily estimate what is the shear modulus of the soil. You can refer to IS 5249/1992 class 7.3.1. there it has given all these values for different types of soil, what is the Poisson's ratio. Now, uh, along with the Poisson's ratio, number of factors affect the shear modulus reduction curves. Briefly, for coarse-grained soil, the modulus reduction curve is mainly affected by the initial voids ratio or relative density and confining effective stress, whereas the fine-grained materials is strongly depends on the plasticity index. So for that, uh, some of the shear modulus reduction curves that has been included in the Shake 2000, these are inbuilt in that Shake 2000 software, but you have to select a particular type of curve depending on what type of soil you will encounter. In the Shake 2000, we will give them as input as an equation number. If you just input the this equation number, then it will select that particular curve. So for sandy soil, this is the curve, and sandy soil again is the same thing. The input, and please refer to the with the fine content greater than paper number 8 here, which I mentioned in the reference parts. So again, along with the shear modulus value, we have to give the damping ratio value for the shake as an input. In a seismic event, during each cycle of loading, you know that energy is being dissipated. As the soil gets strained beyond the linear elastic range, then we have to make use of some of the damping ratio curves, which we have to include in the Shake 2000 analysis. Now again, these are some of the curves. Select Okay, so these are some of the inputs required for us to carry out the shake analysis. So as I told you, we have gone to a depth of 21 meters below the ground level. We measured what is the primary wave, shear wave velocity, density, and the ratio of that, Poisson's ratio, Young's modulus, shear modulus, and bulk modulus. All these things we have calculated. And this window will show you how do you feed into the Shake 2000 software. You have to give what is the soil depths and what is the soil type. Maybe say soil depth, say for a depth of 4 meter, you will have a same soil, means then you have to give the soil type as 111. Suppose if at a depth of 7 meter, if the soil is different, then you can give the soil type 2, like that. Then soil thickness, well, we have to give it as say 1 meter thickness, so you will have a better results if you divide them equally. Then if you give it as a 2 meter or 3 meter as a soil thickness, then you may not be able to achieve a better accurate results. So you split them into 1 meter soil profile, that will be better. So this shear modulus, that this equation number 2 is inbuilt in the Shake 2000, then it will refer to the shear modulus reduction. It will pick up that particular equation. Then the damping ratio also, as I mentioned in the previous slide, it will select what is the damping ratio curve I have to refer to. Then the density also I've given here, 1717 for the soil type 2 is given as 19, and what is the corresponding shear velocity. This you have to give it as an input for the Shake 2000 software. Now, the representations, again, I mentioned here what is soil type 1. In my study, soil type 1 is sandy soil, and soil type 2 is rock soil. And again, I refer to these two graphs. Equation 2 stands for this, and equation 6 stands for this. Damping ratio, equation 2 will be this, and again, equation number 7 is this. Now, this is the window what you will get when you just open the Shake 2000 software. These are the 10 or 11 steps involved when you perform the Shake 2000 analysis. You need to feed in what is the dynamic soil properties and soil profile. As I told you, if you have say 10-meter thickness, you split them into 1 meter, and if the soil is of different type, then call it as soil type 1 and type 2. And you have to give what is the input motion, which earthquake you want to give it as an input motion, then assignment of object motion, everything you have to give it. Now these first 3 or 4 steps are the input motions what you will get it, and these are the output options what you have to give it. From option 6 to option level, what you are expecting out of the Shake 2000. You want to compute the acceleration at different layers, then you have to select that particular one. If you want the response spectra, amplification spectrum, Fourier spectrum, then you accordingly select that. This is all about saving the file and in which directory you wanted to save. You have a number of options here, what plot options you wanted. Accordingly, you can select them. And this is the conversion of the ground motion file from RSP. That means usually when we collect any earthquake data, you will have a single column data. When you download it from say peer earthquake database, you will have a time history as a single base. This will give you what is the total number of readings and what is the time step. And it is a single column, but this shake will not perform that. It should have a multiple columns like this. Then conversion can be done with the help of this shake 2000. You have to define what is the number of time steps, etc. Then this conversion will happen in this particular step. Okay, so now I'll move on to the contents what I explained. Even in the previous micro tremor studies, I told that we have selected some earthquake and we did some analysis. But I wanted to explain what steps you have to follow if there is no earthquake available, then how to proceed and how to do the site-specific response analysis. Now this I have already repeated, zone factor and my expected magnitude of the earthquake 5 to 6. There I mentioned it as 7.5. Between 5 to 7, you can select any magnitude of the earthquake. So I mentioned this already. No records of the strong motion is available in the study area. Development of synthetic earthquakes for the region is necessary. You have to develop synthetic earthquake motions. So what methodology we follow usually is use of strong ground motions available from the historical earthquakes. You have to search for the earthquakes which has happened in the past. So when you select these earthquakes from the past, previously occurred earthquakes, some factors you need to consider. You should search for a similar magnitude. That means if you are expecting an earthquake between 5 to 6, you cannot search for a 3 to 4 magnitude earthquake data. So very close to that is also fine. So peak acceleration close to the target value. Someone would have done some microresonation studies in your particular area. Please look in for that. You refer to some literature. You will get what is the peak acceleration. You can expect it. So match that. When you select the earthquake, you look in for what is the peak ground acceleration value also. Very close to that you select, and what is the similar fault distance and similar site conditions. There should not be too much variations in the soil profile. You have to look for a similar soil site conditions, and you select that particular earthquake. Now, this is one study conducted by Sitaram et al. As I mentioned earlier in my study. I think reference number 1 I missed here. You can refer to reference number 1, where this study has been done for Bangalore city. They have given, depending on the latitude and longitude, they have conducted some peak ground acceleration studies, rock level PGA values. They have given, depending on your place of investigation, you can select that. So we were doing analysis near this particular site. So we had an option to select between 0.14 to 0.15. We have to select our PGA. That means when we look in for an earthquake, that should have a PGA between 0.14 to 1.5. We had that challenge of selecting the earthquake. So earthquake, then we looked in for Boston earthquake, which was having magnitude of 5.9 with the PGA of 0.2 G. Even though we required, we needed 0.14, between 0.14 and 0.15, we have collected this 0.2 G, and we then later stage we scaled it down also. That I'll show you. Okay. So to get the desired PG of 0.15 G and target spectra for 5% damping for rock or hard soil according to IS 1893, we did this response spectra matching 2005. If I get some time, I'll show you how do we do this. See, response spectra matching, Sysmo match, Sysmo signal. There are some softwares available to do this, scaling down. And also, if I get time, I'll just go through that at the end. Sysmo signal, how do we do this? Okay. So RSP Mesh 2005 program was used to scale down the PGA and to generate the spectrum compatible time history. So this was the acceleration time history, what we collected for the Boston earthquake, which was having a bedrock acceleration of 0.2 G. We scaled it down to 0.15 G. We scaled it down to 0.15 G. Okay, so time history of selected scale down motion. Now we use this response spectra matching, and that is how we did this scaling down. Now, once we scaled down, we developed this response spectra. Okay, so you can see here, this was the target spectra what we had with respect to IS 1893. And if you look in for a original motion, what we collected, this was the spectral acceleration variation with respect to period. Then we modified this. This is what you can see in the blue lines. That is the spectra of the modified motion. So response spectra of the selected earthquake motion before and after matching the target spectra for the Boston earthquake. We developed this response spectra for the particular site. Now, moving ahead, we did the site-specific response analysis. Again, the time history, what we got it here, 0.15 G. This was used as an input here. Okay. So Shake 2000 computer program, which again I've repeated many times, an equivalent linear one-dimensional analysis. We do it. Synthetic earthquake motions were specified at the base of the soil profile to conduct the dynamic analysis. So this is the inputs. at the bedrock level what we have given it as, and this is the output what we got it at the ground surface. You can see at the bedrock level, the acceleration value, maximum acceleration value was 0.15 g, but when we collected at the ground level, it got amplified to 0.485 g. Okay, so now again, spectral acceleration, when we consider the ground surface, we wanted to test what will be the spectral acceleration. So we plotted this target spectra, and this is actually the spectral acceleration at the ground surface motion. So this is for 5% damping what we calculated. Now we studied what is the peak ground acceleration and the corresponding amplification factor also. So we define peak horizontal acceleration values at bedrock level were amplified based on the soil profile. Depending on the soil conditions what we had at this AB14 location, the soil, the acceleration values got amplified. Acceleration time histories at various depths are obtained as an output from the Shake 2000. So you can get the output acceleration time history. If you wanted at the middle layer also, you can extract that, or if you want at the ground surface, you can extract that with the help of this Shake 2000. Now PGA value what we obtained is 0.485 g. You can see the variation of this peak ground acceleration with respect to depth here. When it reaches the ground surface, its value was around 0.485 g. So we calculate the amplification factor as the ratio of peak horizontal acceleration at the ground surface to peak horizontal acceleration at bedrock level. So that is what we got it as. 3.23 is the amplification factor what we obtained for that particular site. So amplification factor for most of the Bangalore region was in the range of 2 to 3. This is in agreement with the Sitaram et al. Who did the study in 2005. We have also concluded that most of the Bangalore region has a moderate amplification potential. Now, since my presentation is limited only on site-specific response analysis, as a continuation of this previous work, we tested the bridge structure for we analyzed for response spectra and time history analysis. This is how we modeled in STAD Pro. This is how we modeled in STAD Pro, and these are some of the values. We did this study in both the direction, longitudinal and transverse direction, with different support conditions. Okay, fixed support, pile support, and box supports. Manual calculations we did, static and response spectrum analysis and time history analysis. We did in both the directions, transverse and longitudinal. With this calculation of the base sheet and time history method also. This is these first two figures will show you longitudinal and transverse direction. These two figures will represent the peer deflection in longitudinal and transverse direction. Okay, so this is what is the site-specific response analysis. We have done it for the two places in Bangalore city. Now, once I spoke about the Shake 2000 software, I have to mention some of the limitations what we have in the Shake 2000 also. Over the years, we are using this. Okay, what do we call it as equivalent linear total stress approach. We are following this Shake 2000. But in case of your effective stress, if you want to measure what is the effective stress, then you may not be able to perform the analysis here. The limitations, if I can mention some of the limitations, for strong shaking at some sites owing to non-linear site response effects resulting in large shear strain response, which is not properly captured in the equivalent linear soil models. So, okay. The next limitation what we have is at sites where soil have the potential to develop significant seismically induced excess pore water pressure, then we have to perform what we will call it as deep soil studies, which I'll be explaining in my coming studies, coming slides. So these two are the limitations what we have. Okay, so with this I'll move to the one more software what we call it as a deep soil. Again, this will be used for a one-dimensional analysis also, one-dimensional site response analysis. Okay, so it can perform you one-dimensional linear time domain analysis considering total stress and the effective stress. That is the advantage what you have. One-dimensional equivalent linear frequency domain analysis can be performed here. I'm just giving you the procedure. How do we do it here with the help of deep soil? We are still working on this, and we are conducting again site-specific response analysis with the help of this deep soil. Maybe in future I can come up with some of the results with this. Okay, so this is the deep soil. You can have a analysis analysis motions, predefined motions will be there in this. And if you want to give some other input motions also, you have the options. This is the first window what you will come across. the analysis part, what analysis, whether you want to create a new profile, or if you want to perform the existing one, you can do that. And these are the steps involved in this. Again, you have to feed in the soil layers and what is the damping ratio, etc. So the second window will give you the motions available in this inbuilt motions, what you have. If you want to perform for any other earthquakes, you can just copy that and paste it here, and you can select that particular earthquake. Okay, so different motions available in this. And I'm just showing you one analysis, or the one window where linear analysis has been performed. So analysis step 1, you can see this window. It will ask whether you have to perform frequency domain or time domain analysis. You want to generate the pore water pressure or not, you can select your options. Okay, accordingly you can select. So this is the step 2. In the step 1, you will have this option where you want to do the linear analysis or non-linear analysis in time domain, or frequency domain, that you have to select it. Again, soil profile, as we did it in the Shake 2000, you have to define what is the layer name, thickness, unit weight, shear velocity, and what is the corresponding damping ratio. You can keep on adding. If you require more number of layers, you can add the layers here, and if you want to remove some of the layers, you can remove that. And if there is any water table present here, you can select what is the water table, at which water table, at what depth you have to, what layer level you have to introduce the water table, that you can give it. I'm just showing you one example which is given in this Shape 2000 nonlinear analysis, multi-layer analysis with pore water pressure generation. So the steps involved here, again, to begin with, since I mentioned it as nonlinear analysis, we will select this option. Also, it will give you the equivalent linear results also. If you just click on this, it will give you the equivalent linear analysis results. So since we are discussing on the generating pore water pressure dissipation, bottom of the profile, what type of boundary you have to select it, and what type of soil model you have to select it. I'll come to this, what is DS, NL1 and all. So accordingly, that you have to select it. So what is this? What are the different types of models available for you? If you want to perform frequency domain, that you have to select it here accordingly. DS flow frequency domain, and DS ELO means frequency domain equivalent linear analysis, and DS NL1 means time domain nonlinear massing rules and all those things. You can select pore water pressure generation and dissipation also, you can select it. And some layers I've just shown here, some of the layers whose thickness, unit weight, shear velocity, everything. You can refer to the manual what is given with this deep soil. Some of these are default values what you need to select it. Okay? And conversion of unit, either you can do it in feet per second, feet, or even in meters also. That is from English to metric units also you can do it. And if you don't have the shear velocity values, if you have the shear modulus, that you can convert here, velocity to modulus, or from modulus to shear velocity. That option is available in this. So this is step 2B, what I'm explaining here. Once you give that soil profile, it will show you what is the variation of shear velocity, frequency, strain, small strain damping. All these values will be shown here depending on the layers, how many number of layers you have defined it. Now again, you have the option of selecting elastic off space or rigid off space. Okay, so the shear velocity, if you know all these details, you can give it what is elastic off space and what is rigid off space is mentioned here. And if you have any bedrock motions, or if you have any standard values of unit weight and shear velocity, that you can give it as an input here. And they have selected some earthquake data. In step 3, you have to select a particular earthquake. You have an option of, you can select even multiple earthquakes also. You can see here damping ratio is given as 5. You can select multiple options, multiple earthquake motions also. Accordingly, it will give you what is acceleration, velocity, and displacement for that particular layer of the soil. Then this is Fourier transform function with respect to frequency, and what type of damping matrix, Rayleigh damping you want to select. You can select that. Then define matrix with modes, etc. Number of modes to be considered, 2 modes or 8 modes you want to perform with. All those details are available here. Now, the number of iterations, what you have to do it in order to get this in terms of frequency domain. If you want, then if you want to do it in time domain, what is the maximum strain increment? Okay, so time history interpolation, either linear interpolation you wanted to do, or zero padded frequency domain interpolation. That is step 5 in this deep soil analysis. Now, once you give these input data from step 1 to step 5, Now it will ask for you to analyze that. Once you analyze that, you will get this total acceleration, relative velocity, and relative displacement. You can select whichever the options you wanted. Time history plots, if you want, you can select stress strain plots or spectral acceleration. Or if you want response spectra summary also, you have an option to select here. Okay. So again, stress strain plots, you can see here. This is stress strain ratio, shear stress ratio versus shear strain percentage. You can select here, and spectral plots, spectral acceleration versus periods, Fourier amplitude versus frequency. Okay, Fourier amplitude ratio versus frequency. You can even get it from this, and this is peak spectral acceleration, pseudo spectral acceleration, what you will call it as. So this was the input motion. What you got this is at the layer one. Layer one means at the ground level. Okay, you can say that it has been amplified. Okay? So this is the input, and this is the output. What you got it as. And this you would have seen in the morning presentation, the triported plot. You can construct your pseudo spectral velocity, displacement is present, acceleration is present, and period also. You can select this. View tripod, that option is available in this. You can readily use this as a guideline. So with all this explanation, I wanted to conclude my presentation. One-dimensional ground response analysis was carried out at a different location, has revealed that the peak ground acceleration value was ranging from 0.3 to 0.44, or maximum say 0.5 g. Okay? A maximum spectral acceleration of 2.07 g has been observed at Vijayanagar site, corresponding to a time period of 0.17. So the another advantage what we have with this refraction microtremor studies is based on the shear wave velocity. As per the international building codes, it has given some classification based on the value of shear wave velocity, whether the site is class A, class B, or class C. It's indicating that whether the soil is dense or soft or something like that. So based on the shear wave velocity, what we performed from the refraction microtremor studies, we got the shear wave velocity taking into consideration all these sites. We got the shear velocity between 378 to 603. So as per the IBC 2006, we classified the site as class C. That means very dense soil and also soft rock. An assessment of liquefaction potential also did at the selected site based on the measured shear wave velocity values, indicated that these sites are free from liquefaction. Now, as an addition to this, what I discussed in the first three, with the help of your refraction microtremor, you can even estimate what is the bearing capacity of the soil also. Okay, you can estimate using the relationships available. You can estimate based on the measured shear wave velocity. You can find out what is the bearing capacity of the soil also. Now, with respect to the second case study, what I explained, site-specific response analysis was carried out at the Chinnaswamy Stadium. It showed that peak ground acceleration was 0.485 g. Here it was 0.44 with an amplification factor of 3.23. And the mode analysis for Metro Rail Bridge was carried out using STAD-Pro, considering fixed base, pile support, and underground station box. With consideration of local site effect, shows that natural time period is primary parameter which regulates the seismic lateral response of the bridge structure. So you have to conduct the site-specific response analysis before you take up any construction activities. Particularly important structures, what you call it as tall structures, or nuclear power plants, or you can take into consideration these metro rail bridges. Instead of depending on the response spectra what is given in IS 1893, better if you perform the site-specific response analysis with these available softwares. It will be giving you better performance of the structure. Now, before I wind up, I would like to give you some comments. These two methods what I mentioned, the Shake 2000 or the deep soil, what we used. Again, in both the cases, if you see, we have given the input of the soil layers here. If you just check here, we have given the thickness as 10 meter, 15 meter, or 20 meter, or 25 meter, something like that. What happens if the soil layer is not horizontal exactly? I'll just draw you and show. Suppose if I, 1 second, I can just check whether I can edit this or not. Suppose if the soil layer is not exactly horizontal or somewhat like this, then how do you feed in this in your Shake 2000 or deep soil? So this has to be overcome. You can overcome this with the help of available finite element softwares, as I mentioned. So even some of the boundary conditions also can be defined properly with the help of finite element methods available. Okay, so it's not that you should not use these